Hello, and welcome to the technical video for the project 3D Space Printers. My name is Marco Montero, and our goal was to increase the strength of 3D printed parts to make it a more reliable and sustainable option for long-term space travel. We did this by working on joints, basing our project on a previous model built by another team. They had built a rover out of 3D printed parts, and in one of the supporting arms, one of their joints suffered a structural failure. So we decided to focus on different types of joints and how we could find the strongest type of joint. We started off with small cylinders of different joint size. We worked on ratio with a ratio of 20% or 0.2 centimeters to 1 centimeter diameter for the cylinders, and working our way up to 4% or 40%, 60%, 80%. Trying to see which ratio of pin to cylinder diameter would be the strongest. Later, we decided to scale up to more aptly represent the joint we were trying to emulate. The rover the previous team had built had a diameter of about 1 inch, causing us to build different designs with different diameters: 2 inches, 2.5 inches, and 3 inches. Just to be able to get a wider range of data points. We were testing how resilient they would be to stress, both applied vertically or stress parallel to the joint, or horizontally, where the stress would be applied to the center of the joint, pulling it down. Testing these two methods would give us a general ballpark for how resilient they would be to gradual increases in stress. By adding stress little by little in particulates and through a bucket, we were able to get a gradual increase in the stress until the joints broke. The horizontal test had an extra factor that caused the joint to fail at an earlier weight. Since the joint was a certain distance from the points of attachment on the table and the mass was pulling it down, there was an added torque force with the distance from the pivot point added to the joint, causing the joint to fail at a sooner point. Different sizes were tested, multiple samples per test, and we were able to gain a good understanding of what ratio would be best. In the future, we would be able to continue not only testing the ratio of diameter, how big the pin is compared to the cylinder, but also how long the pin is. Right now, we worked with a 1/5 ratio. Each cylinder, starting off with the small cylinders, was 5 centimeters, and the pin was 1 centimeter on one side, 1 centimeter on the other. 2 centimeters in total, with a 10 centimeter cylinder in length. Over here, since in total it was 20 centimeters, each pin was 4 centimeters, keeping it at a 1:5 ratio. And yes, future testing will be needed to be able to find the ideal pin, but much progress has been made.